The Symbolic-Branch Collatz program aims to determine the exact topological entropy of mixed-branch dynamical systems. We are looking for the underlying mathematical law that forces seemingly chaotic orbital paths to lock into a unified, predictable growth rate. We can observe this behavior by examining the period 4 symbolic sequence defined as epsilon equals 1110. This chart shows the numerical iterates of the cylinder counts for that sequence. The initial values scatter erratically across the plot, but as the iterations continue, they rapidly flatten out, locking into a smooth horizontal asymptote. If we zoom in on that limit, we find that the dominant growth rate stabilizes down to 13 decimal places of precision. Stability to 10 to the negative 13 is not a rounding error or an artifact of numerical estimation. A number that stable dictates the presence of an exact, rigid mathematical structure governing the entire system. For simpler sequences like 1, 0, 1, the entropy can be solved using a scalar Kraft-identity approach. For 1, 1, 1, 0, that method completely breaks down. Applying finite state logic partitions the space into two discrete nodes, roll B and roll C. A continuum channel evenly maps mass across the target. But the immediate return channel acts differently, abruptly collapsing mass from both nodes onto a single point, the invariant core X. This creates a structural anomaly. Once a path enters roll C, its valid future moves depend strictly on whether it arrived via the wide continuum channel or the collapsed point. That hidden memory requirement destroys the Markov property. A standard finite state generating matrix treats every arrival at roll C identically, meaning it will inevitably overcount the number of compatible paths. To correctly track this sequence's history, we must abandon finite state Markov codes entirely and construct an infinite dimensional operator. We require an age-structured operator, denoted as capital T. This operator must track finite atomic measures simultaneously across the discrete rolls and across continuous in-flight excursions. This diagram shows our new Banach space. We start with two solid domains representing the discrete populations, B-pop and C-pop. We then add a third component, the A-pop continuum. Instead of a discrete block, this is parameterized continuously by age, marked here as T. We can now map the exact one-step evolution of the system. Units of mass from B and C return directly to the invariant core within C. At the exact same time, B and C units launch distinct individual seeds outward into the continuous A space. These seeds age, advancing continuously by a multiplier of lambda. The moment their age reaches a specific mathematical crossing bound, they exit the continuum and route right back into the discrete rolls. Because this algebraic construction continuously parameterizes age, it perfectly isolates the individual history of every seed. The Markovian overcounting obstruction is completely removed. With the space mapped out, we formally decompose the operator into two parts, P plus Q. P is a rank 1 operator. Its sole function is to extract the mass returning specifically to the invariant core X. Q handles the remainder of the system, governing all the aging mechanics and delayed transitions through the continuum. By applying a specific weight norm that tracks the total variation mass, we can strictly bound the essential spectral radius of Q. This chart shows the complex plane for our operator. The essential spectral radius of Q is bounded by this circular region, marked gamma, locking in at approximately 1.388. Our system's overall growth factor, lambda, is larger than gamma. Therefore, eddy spectral activity existing outside this bounded disk is mathematically guaranteed to be an isolated, finite multiplicity eigenvalue. This setup allows us to apply the rank 1 resolvent identity. We set the scalar function f of z equal to 1. Because P is a rank 1 perturbation, finding the complex eigenvalues for the entire infinite dimensional operator is reduced entirely to finding the roots of this single equation. The massive structural complexity of this infinite dimensional Banach space has been compressed down into one solvable algebraic equation. Evaluating the resolvent identity yields an exact result. F of 27 over 16 equals 1. This places our point perfectly at 1.6875 on the positive real axis, well outside the gamma boundary. This proves that 27 over 16 is a genuine eigenvalue, and it yields a strictly positive eigenvector. This chart shows the characteristic equation, d of z. To verify the eigenvalue is algebraically simple, we evaluate the derivative at lambda, revealing a steep, strictly positive slope. Because that derivative is strictly greater than 0, the eigenvalue is mathematically confirmed to be a simple 0. We also observe the phase alignment across the system. The greatest common divisor of the return lengths is exactly 1. That coprime phase alignment mathematically rules out the existence of any other eigenvalues sharing the same magnitude as lambda. The system possesses a unique, simple, peripheral eigenvalue, separated by a genuine spectral gap. Going back to our initial chart, the Perrin decomposition shows us exactly why this happens. Iterating the operator creates a rank 1 projection growing exactly at lambda to the n, plus a remainder error term that decays exponentially. That mathematically rigorous exponential decay is the direct cause of the 10 to the negative 13th numerical stability we observed at the very beginning. Using spectral duality, we can extract the core cylinder count growth rate directly by taking the inner product of the operator iterates against our initial root state. This spectral transfer completely bypasses the need to estimate independent domain counts. The math provides the exact rate. Because the core root rate governs the total systemic rate, taking the limit of the full mixed system gives us our final answer. Where finite state logic broke down, moving to an age-structured Banach space isolated the true growth mechanism. The spectral gap dictates the exact topological entropy.